Try again. Hello, everybody. Any better? Probably not.
Okay, it works.
It works? Yes. Okay. So this is a talk about something I've been curious about for a very long time, since 2007 actually, about whether interesting things happen if you interfere with an encrypted channel in a really dumb way, that doesn't assume knowing anything about the channel. So I was curious about this since 2007, and until DARPA Cyber Fast Track actually financed this, and we did some studies with the company called Milcord and found out that indeed there are some really interesting effects going on, even if we don't understand what exactly is happening. This talk is about really simple ways to interfere with encrypted traffic. Basically, you lose you drop every end packet, and you end up with a signature. It's as simple as that. And our educated guess is that the reason this is happening is that there are all kinds of interesting behaviors produced by the fact that the packets go through multiple queues, and that the more complicated the system of queues is, the more interesting the signature becomes when you start interfering with the queues. We have some suggestions as to what to do to make things look a lot less interesting and a lot less fingerprintable. This is how it looks if you're looking at fast traffic. So these are two signatures of two different ciphers using IPsec and SCP file transmissions going through IPsec. As you can see, the dots here, which we will explain in a moment, are clustered in completely different places. The clusters are of different weight. This is the same stuff with the OpenVPN. We drop each fifth packet. Suddenly there are signatures. So these are timings of 100 of packets added together. As you can see, AES looks completely different from Blowfish. This is like visible with the unarmed eye. This is still work in progress, and unfortunately we were not able to explain a lot of things that are going on. But we think that this is important because this is something that has not yet been explored and discussed.
And you should also regard this as an invitation to join us in this exploration.
So how did I discover this effect? In 2007, Dartmouth College hosted the Democratic primary debate. So normally this should not affect normal humans. So there are crowds of people online, there are crowds of people on campus, and the network is somewhat more congested than usual. But you don't expect much to happen to affect you personally, except my SSH stopped working. And it didn't start working even after the television crews left the campus.
So what happened was...
that the network people decided that they were going to be really helpful to the television crews and to give priority to the streaming video. But it turns out that the Cisco algorithms for quality of service are not as good as you would like, and that when configured improperly, when your SSH gets really low priority on those, they start doing really bad things to traffic like SSH, because what they do is delay each end packet, for example. And TCP doesn't work well with that, and SSH works even worse with that. You basically cannot use your SSH anymore. It took a while for our sysadmins to solve this problem. And by this time I was curious, what else can you do if you just drop or delay each end packet?
For example, can you allow through normal web browsing, but totally ruin anything encrypted and make it so painful to use as to being impossible to use? And the answer is yes.
What we've seen in the wild suggests that the answer is yes.
So let's talk about packet timings. By the way, I talk more at these conferences, but this is really Anya's work from start to finish. All I did was write a few shell scripts, so I am basically just enjoying the support role here, the vocals. So there has been a previous work that looked at round-trip times and what they can tell about routers, about the network. There is a talk at DEF CON 11 by Tony Capella called Fashionably Late, what your RTT tells about your network. And the idea there was that you ping your router as fast as you can, and then you look at the round trips. And by filling the queue of the router, you can actually tell how deep that queue is. So you see this sort of a saw pattern in the RTT. When you fill the queue, and then when it clears, and when you fill it again. So there is this periodic pattern that tells you what router it is, what size of a queue, in so much as what size its queue is. This has been used for network scanning. So there was the port bunny in kernel scanner that was much faster than Nmap at the time. Nmap since then improved. This was done by Recurity Labs, by Fabian Yamaguchi and Felix Lindner. And the little port bunny, pink bunny, is their artwork. So what that did was it looked specifically for that saw pattern when some buffer on some hop, on some router, got saturated and eased off. And so they were able to finish their scan without losing packets to the overfilled queues. And they could do in 15 seconds what the Nmap took tens of minutes to do. So these are known effects. What's less known is how the advanced features of TCP interact with file transfers. So this picture is from Stuart Cheshire's study of how the combination of the delayed ACK and the Nagel's algorithm in TCP caused this kind of packet timings. So this was done with TCP prof, and a transfer of a large file would just stop for 200 milliseconds doing nothing in the middle of the transfer. Then ramp up, then again, then again do nothing. And why is that? It's a combination of two behaviors. First, the delayed ACK. So when you imagine an interactive session, your kernel doesn't actually ACK a segment coming in right away, because the kernel thinks, well, this looks like an interactive session, right? So we'll wait for 100 milliseconds or 200 milliseconds till the application actually gives us some data back. Because, say, SSH would echo back every character, right? So we'll just wait. And if the application doesn't send us any characters, then we'll send the ACK back after the timeout. And if it does, then we'll send that data with that ACK back. And so you'll save a packet that way. So this is the delayed ACK. And this happens when only one packet arrives. If two packets arrive, the second one will be ACKed immediately. And then there is also the Nagel's algorithm. You don't want to send short packets to the other side. If you already have packets in flight and they have not been acknowledged, and you have a short buffer, then you just wait. Again, 100 to 200 milliseconds till either an ACK arrives or more data is given to you by the application. So when that happens, you send the larger packet. If an egg comes, then you send whatever you had. So both sides then have wait behaviors. The kernel actually sits and waits, hoping to save you a packet or an egg. And this causes the bulk transfers to get completely screwed up like that. I mean, imagine, you're waiting half the time that it takes you to transfer the file. And this is just one example of the interaction between the layers, like the kernel and the application layer. Now, if you add VPNs to this, right? VPNs have their own optimizations and queuing and timeouts. So if you control the gateway, say you're an ISP, then you just basically start eating up packets, and you can tell by the timeouts just exactly what kinds of combinations of queues are on both sides. So this is important. You can profile these things, and you can fingerprint these things. So if you are an ISP, or if you are an organization that controls its own border router, and you have this encrypted stream crossing your border, and you don't know anything about this stream, you don't even know how it started, you could start interfering with it, and by watching its timings, learn about what that stream might be. And that, you know, if you actually have a duty to protect your border. Now, of course, if you're an evil ISP or an evil gateway, you can use the same thing to try to link streams of unknown origin to see if they come from the same kinds of software stacks. And you could try to find out things about those streams. And one thing that Anna found is that you can actually tell the cipher of the enclosing VPN pipe if what you use inside that VPN pipe is TCP and SSH, that is to say, protocols with a rich behavior and rich interplay between the layers. So, and that you can do only by measuring packet timing, because crypto libraries have their buffers.
So the experiment is actually really simple. You transfer a long data file, and you drop each fifth data packet, just like that. And then you time, for example, 100 data packets together. And this absolutely dumb thing, it gives you a signature.
Yeah.
You get the signature just for dropping each fifth packet and adding 100 data packets to the timings of 100 data packets together.
And by the way, you see my contribution to this.
Practically for free, right?
Yes. And you see my contribution to this right there on the screen. That IP tables line.
Signatures from a fast network. So 4 different ciphers. You can see they look hugely different. By the way, if you repeat the experiment, you get the same proportions of dots in each spot. So these are timings of 100 of packets together. So,
oh, maybe I'll serve as the designated pointer, right? So
there are 3 clusters, and down below the green line is the same traffic if you don't drop any packets. So if you don't drop any packets, then this OpenVPN traffic looks exactly the same for all the ciphers. But once you start dropping them, they start looking hugely, hugely different.
So this is a normal gigabit network. It works best on fast gigabit when there is no contention. So this is basically what you get, the timings that you get per 100 packets every time when you don't interfere. And when you start interfering, you start seeing that the 100 packet timings actually split up into clusters. And the clusters are differently populated. So if you look at this as a sort of, okay, let's just project everything onto the y-axis and make like those dots that you're getting are actually stripes. And you color the stripes according to the intensity. You know, the intensity is the side of the cluster. You can sort of see this as a spectral picture. And, well, you can't actually see it, but there is this cluster there at that arrow.
More about AES in a moment,
Yeah.
because AES is actually kind of special, as it turns out. So AES is actually the closest thing to the unencrypted traffic, at least on OpenVPN UDP. So, and in other places we looked, it was also, for some reason, the closest thing to unencrypted traffic. So the scale is different there, but these are, so like those two red lines below for AES are the same two red lines as are there for the unencrypted traffic with each fifth packet dropped. So this is for OpenVPN.
Yeah. So what we did with OpenVPN, we configured it to use AES CBC, which is its normal method, and then normal configuration. And then we configured it to use no encryption, the null cipher. And so, again, the green line is the undisturbed traffic. The red lines here are the traffic that has been disturbed with every fifth packet being dropped, and therefore you get all of those retransmission mechanisms in place of the OpenVPN and of the TCP IP and the SSH, UDP, playing into this. So you see those two clusters due to some interaction between the layers. And then one of those clusters splits if you're starting to use AES. It's as if you're applying, a prism to a ray of light, and then, you get
weights of those three clusters that we observed on different ciphers and on no encryption. No, the unencrypted one is at the end. So as you can see, the proportions with AES are closest, except for this extra green thing.
So there is something to see here. First, even if you don't use any encryption at all, you just use the native queues of, you're still seeing the native queues of
just
your
OpenVPN, even with UDP.
Right.
So the OpenVPN already gives you some interesting behavior just by itself.
Right. And then if you switch it to a cipher from the null cipher, then you actually get very different sizes of those clusters for different ciphers. So just because you have a file transfer and this packet dropping behavior, your cipher shows statistically. Isn't that interesting? I mean, you're not learning anything about the data being transmitted, but you're learning about the pipe. And so you can link, say, two instances of the pipe to each other, for example.
Well, obviously, OpenVPN is a bad case or a good case because it has a complicated behavior. So IPsec has a simpler behavior. But we still get signatures even there if we use SCP to transfer the files. So the same experiment, drop each fifth packet, time 100 packets together. But we notice that in this case, a lot of ciphers start looking a lot more similar than they look for the OpenVPN.
So think of this architecturally, right? OpenVPN, of course, is a user-land process that gets its packets from the pseudo interface, the TON interface. And so, your packets get out of the kernel and then get written back to the kernel. That's quite a bit of cross-layer interaction and store and forward and buffering and that sort of thing. Now, IPsec is in the kernel, right? It's, between your second and third layer, however they put it. So in order to elicit some behaviors, you need some other store and forward schemes involved, some other buffering schemes being involved. But, even if you're on a VPN, how do you transfer a file? Do you do an FTP? No, you don't, because that's, you're cursed if you do, right? So you use SCP, right? And you use another layer of encryption. And that layer of encryption, and that another layer of reliability, if you have that, gives you that behavior enough to fingerprint the pipe.
What happens if you use netcat? Well, congratulations. So the green stuff is SCP, the red stuff over there is netcat through IPsec. The signature is gone. So you can't see anything anymore. So just like use netcat through IPsec, and nobody will be able to find out what cipher you're using. There are no signatures.
And that's netcat with UDP transfer. I mean, this is the simplest protocol that can ever be, right?
We've eliminated the signatures. Chaining mode doesn't care. So as far as chaining mode is concerned, this fingerprinting algorithm can't tell the difference. The results are the same. As far as it can tell, this is the same cipher.
And also notice, this is Rindale, this is AAS, right? Slightly different.
Okay, so now when you actually go to slow networks, you end up with a lot messier results, which you will probably have to run through Fourier transforms in order to actually get something useful out of that. That messy. But you can see that the periods are kind of different and that there are things going on, and just that it's a lot harder to tell what these things are.
So it really seems to be about the queues. So say if you look at the VPN that is a userland VPN, such as OpenVPN, right? You have your TON device and you have one layer of TCP or UDP that goes into your VPN. Then it goes into your VPN transport. And then, it's whatever application that you're using to transfer files. So in each and every layer of this, you're eliciting some result. Now, I'll return to the slide for a moment. So if the block sizes are the same, if the chaining mode, if the queuing of those blocks is the same, as is the case with Rindale, which became AES, then some things don't matter, and you get the same signature. But basically, this is a really nice way to say that these things are implemented very similarly. Whereas when you have other things such as SCP versus netcat, or say OpenVPN versus IPsec, they are quite different, and they show that way.
Some things that we tried did not work. I had great hopes for delayed packets, because this is how Cisco ruins your SSH. It delays each nth packet, and you're screwed.
Misconfigured Cisco. We are not ready on Cisco.
Unfortunately, if you take a fast network and you delay the packets, then your packet arrives after the end of the transmission, and you're basically just losing that packet. And slow traffic is a lot harder to figure out than fast local traffic. So random drops don't work. You basically get the really mixed up picture as if you were dropping n different patterns. So the first packet in n, or the second packet in n, or something like this. So you get a sum of different pictures.
So what happens there is that dropping nth packet gives you a slightly different pattern depending on the n. And if you drop packets randomly, then you get a mixture of all of these, and there isn't really much to do.
No, it doesn't. It gives you the same pattern, just shifted.
Well, what do I know? It's your work.
So, and the last thing, so may this be a warning to all of you. So don't, if you actually want timings of your traffic, you can't filter packets when capturing, because you end up with bogus timestamps, as it turns out. So don't do that. Filter them after you capture.
Yeah, BPF is killer.
So
BPF.
you end up with packets in the wrong order and with timings that don't make any logical or any other sense to you whatsoever.
It stands to reason because BPF is its own virtual machine, right? That runs over the kernel buffers, runs that bytecode that your TCP dump compiles over those buffers, and it does introduce yet another layer, which is more complex in its buffering than any other. But when we first saw that, we were like, no, our result is lost. You know, all is, it's the end of the world, pretty much, or the end of the project. And then I called a few people and said, well...
Then we were like, how come our packets arrived out of order that they were captured in, or something like this?
Yeah, and they're like, nah, you shouldn't be using BPF.
Don't do that. So
Yeah.
don't ever do that. Capture first and filter after. So what's going on? We don't actually know that. So there might be the timings of how long the cipher takes to do encryption. It might be partially the cipher block size. Or it might be something about the packet fragmentation.
Well, the Rindale versus IaaS suggests that block size and what you do with the block matters. Although if you do just about the same thing, then you know, it doesn't. Fragmentation, there have been attacks on IPsec using packet fragmentation, and we know they work. They actually exfiltrate a lot more than the cipher. So that's probably a thing.
So we made a few profiling attempts to find out exactly where the time is lost during the algorithm. And there actually are interesting patterns that emerge, but we're still not ready to make any claims about this.
Well, let me act as a laser pointer again. How am I doing as a laser pointer? Not very sharp, am I?
So on top of this, this is without packet drops, and on the bottom there is this traffic with packet drops.
So this is an SSH transfer, instrumented. And on the x-axis are functions. Hey, this is magic. Or I can play the cat and like go jumping at the
Play
board.
the cat and chase the laser pointer.
Yeah. Anyhow, oh well, thank you. So anyway, so you see, there are some functions that give you a significant spread of their timings. And again, this is what SSH does, how it reconstructs its own stream. So when you hit it with a packet loss pattern, then you see that those timings spread into several clusters. So whatever was taking time and whatever was varying now varies a lot more, and it values discretely. Isn't that interesting? I mean, the fact that we saw the clusters that were tight enough, well, now we are seeing that with just a standard SSH, and it's, you know, read so many bytes off of the stream routine. And so the functions are packet read sequence number, packet read expect, and that sort of thing. So you sort of see that the a cluster of that was really tight spreads, and it spreads discretely. You know, it doesn't spread all over the place as you would expect with, say, you know, a normal distribution or something like that. So we're triggering some cross-layer interactions. Yeah, we don't know which ones yet.
So you saw these nice straight green lines which occur at unperturbed traffic. And everybody kind of assumes that all ciphers look the exact same way on a VPN, right, timing-wise. But just because you don't see a signature, it doesn't mean that you're not going to get it if somebody does something as dumb as drop each fifth packet of your traffic. Also, if you're really concerned, you might want to think twice before using SCP inside your VPN, or like whatever the double encryption algorithm, and the streams inside streams.
Yeah, so TCP over TCP is again a known bad thing to do. So when you run your VPN through SSH, people tell you to not to, because TCP has its reliability, its packet loss mitigation mechanisms, and when you play those two copies of those mechanisms against each other, you get much worse than the delayed ACK versus NAGL that we touched upon. So usually they say SSH is a poor man's VPN. But it turns out that even if you don't do TCP over TCP, even if you do a TCP transfer over OpenVPN, which uses its transport, which uses UDP as its primary transport, unless you configure it to use TCP, you have very clear fingerprintable behaviors. Very clear interactions. So double encryption considered harmful. And if you're sure of your pipe and you don't want to disclose anything about your activities whatsoever, including what cipher you use or what software you use, then you're best with having just one encryption layer. That's the sort of paradoxical takeaway there. And this is work in progress. So we're going to...
most importantly, we're going to figure out what to do with slow networks and exactly how much information we can get in a real situation, as opposed to a situation with really fast traffic.
Well, we were able to fingerprint a connection from Boston to San Francisco just by averaging the pattern. In fact, how much time do we have?
20 minutes.
Okay. Well, we can talk about that slide. Why not? We have 20 minutes. Okay. Well, apparently not.
So.
So what we want to do is a prototype VPN for being unfingerprintable despite those things. The hostile, the VPN to use in the hostile environments. Other people are working on doing that in real hostile environments, right? So you have quite a number of projects of that kind. But we're looking specifically at timings and specifically at queuing. So, eventually they might be able to pick it up.
There are thanks.
Yeah, there are thanks. I'm being thanked for the scripting. And Milcord has done quite a lot of network setup for this. And our students, Max
done all kinds of things.
and David and Yuzi, have done a lot of experiments so that we could actually confirm that the effect exists and is not just a fluke.
And this is the DARPA challenge coin, the Cyber Fast Track challenge coin. For whatever reason, it has a cat on it, as you can see.
Yeah. So the cat impersonations,
So thanks to Maj and
thanks to
DARPA.
Maj for making this possible. If you and this is it.
Thank you for listening.
Questions?
No. Let's get you a microphone.
Okay, so I'm assuming you did play around with the block sizes. I mean, as witnessed by AES and Reindl. Did you know? Sure, the algorithm too. Did you mess with the key size at all to see if there's any difference between like AES 192, 256, or 128?
Yeah, we had experiments with different key sizes.
Okay, and they were okay.
Take the microphone.
But did they, like in the case of AES, I guess I'm curious if you changed the key size, was that still very similar to the null cipher then?
I'm
Or if it
trying
was-
to recall if we have a comparison. I don't remember. I can look it up for you later.
Okay, I mean, if you're going to
So-
publish work that like has an entire table, that'd be awesome.
So,
Yeah, that will happen. For now, we have a GitHub account with the reports and the scripts, and that's public. Look in Anna's
so
name.
there are very few results there still. So there are no. I don't think these made it. So I don't think the different cipher sizes made it.
We definitely tried them, right? I
Yes.
remember we had the.
So, what was the other question?
Any other questions? Okay. Thank you very much. We will reconvene in here at 3 p.m. Next talk will be at 3 o'clock.